Okay, good afternoon. Let us start our lecture. So, in the last lecture, we talked about something called total probability. So the idea, in fact, all these probability are quite intuitive. So it's saying that, okay, if you can partition the sample space or the possible outcomes into different events, AI, which are mutually exclusive and exhaustive, okay, that means there are no overlapping and put them together is equal to the sample space, then the probability of any event B is equal to the sum of the probability of B given AI times the probability of AI. So in other words, if we have this A1 up to AN, which are partition, when we use the word partition for a sample space, it means two things. All these A's, when you put them together, is equal to S, and any of them have an intersection which is empty set. So maybe drawing a picture will be easier to understand. So these are the various A's. All right? So then for any event, you can think of it as a union of A1 intercept B, A2 intercept B, up to AN intercept B. All right? Are they mutually exclusive? Are all these mutually exclusive? Is this intercept this equal to empty set? Yes. Think of it. Any elements here, it belongs to A1 and also B. Any elements here must belong to A2 and B. Oh, they all belong to B. Fine. But then you have to find something that common to A1 and A2, which is non-exist according to what we are given. So all these intersections should be empty set. So they are mutually exclusive. Then probability of B is equal to the sum of all these probabilities. All right? You see, I try to give you an idea how we got this formula. So the formula seems so complex that you may give up. But in fact, the idea is very simple. All right? It just partition the B into different parts. And because they're mutually exclusive, so probability of B equal to this one. So each of this one can be written as, probability of B given A1 times probability of A1. Probability of B given A2 times probability of A2, and so on. All right? So that is the formula for total probability. Now, then you may ask, hey, this is probability of A1 intercept B. Can I write it as probability of A1 given B times probability of B? Can I write it like that? Yes? No? I don't know. Can we do that? Can we write it like that for that particular? Okay, yes, you can write it like that. But, a big but, it's no use. Why? In order to use, to get this, what do you need to know? You need to know probability of B. All right? And also this one. Unless you are going to use this formula, try to set up an equation with probability of B as unknown. Otherwise, you are writing down, I'm trying to get probability of B, which you give me a bunch of things, and one of them is probability of B. All right? So it may not be a very practical way to get the answer. But I'm not saying that's wrong. It's not wrong. And also it may be useful because you can set it as an equation as probability of B at unknown. Unknown equals something times the unknown plus something times the unknown. But of course the problem is that at the end it's not an equation, it's an identity. Hey, what is the identity? What is the equation? Is this an identity or an equation? Identity means it's always true. This is not true for any other x value except x equal to -1. Then the left-hand side equal to the right-hand side. So this is an equation. All right, we try and find some value of x that this holds. All right. Can you give me an identity? That's the identity. No matter what your x is, so long as it's a real number. Then x plus y square, x plus 1 square is equal to x squared plus 2x plus 1. True for all x. So that's identity. All right? Okay, too much for that. So this is the total probability, and we also briefly talk about Bayes' theorem. All right, Bayes' theorem. So this is the Bayes' theorem. So this Bayes' theorem basically saying that, okay, if I know I want to compute, or I know that event B has occurred, what's the chance that AI has occurred? If you think of it as the picture that we used, so these are the A's, all right, partition, these are all the A's, and this is the B. This is the part B. So P come from here, come from this part, come from this part, all the parts that belong to B as well as belong to one of the AIs. So now we are told that, okay, B has occurred. Okay, so the sample points come from B. So how likely it is from A1, or how likely it is from AJ? So that's what Bayes' theorem says. Okay, what's the chance that given B, what is the chance of AK? Oh, another very complicated formula. But if you understand it, this is nothing but just a conditional probability. By definition, is AK intercept B over probability of B. Probability of B equal to this one, but just applying the total probability. So you don't have to remember this formula, you just have to understand it. Okay, so the numerator is the intersection of A, K, and B. So I write it in this form. All right, for the AK times for the B given AK. All right. Okay. Now, let's look at some example. So suppose there's a chance newly construct house collapse. All right. And it will collapse. I mean, it has a chance collapse whether the design is faulty or the design is not faulty. So the chance that design is faulty is 1%. Right. So in other words, in this problem, we're talking about two events and their complement, of course. The first one is about the design. All right. Whether the design is faulty or the complement, the design is not faulty. Something wrong with the design. All right. Then the second one is the house collapse. All right. So we are given all these numbers. Now, so in dealing with problems like this, you have to do two things. First of all, you have to identify the complement, the events, and of course, including the complements. So in this case, there are only two events. The design is faulty and the house collapse. Of course, including their complements events as well. So altogether, there are 4 events. Secondly, you must link the numbers given in the question or the probability here in terms of percentage. Okay, translate this into a probability statement related to the events that we have. So for example, this 1%, all right, referring to the probability, okay, let's say the design is 40. What number, okay. So we're saying that design is 40, I represent it by B. So probability of B is equal to 0.01. So I have to link up the event that we are talking about and the number is given to us, 1%. That means 0.01. Okay, then how about this 75%? 75%, 0.75. What is it? It is the probability that a house collapses. If means condition. Condition on the design is 40. So in other words, it is, let A be this house collapse is an event A, all right? Design is 40 is event B. Given the design is 40, then the house collapse. So if the design is 40, it's likely that the house collapse. So it's 0.75. Otherwise here means that the design is okay, not 40. So it is B complement. Otherwise, that means B complement. Then this one is 0.0001. All right. 0.01% means 0.00 with 3 zeros, 1. Right? So before you okay, don't try to get all this. There are 3 numbers here. Try to multiply them, one of them, put them, 2 of them together, multiply them, and then get the answer. No, you must be able to explain why you do that. So I have to write down the events, write down the corresponding probability. From all this, I can tell, for example, what is probability of B prime. That means the complement of B. That means a design is all right. So it will be 1 minus the probability of B. All right. How about how come this 2 does not add up to? It's not equal to 1. Why? One is 0.75, the other is 0.0001. One is B, the other is B prime. B prime is the complement of B. How come they are not adding up to 1? Very simple. The event that we are talking about, in the first one is still A, but condition on something. The second one is also A, not A complement, it's A. So, and also the condition now is different. So there are 2 different things, just like comparing orange and apple. All right, one is A condition on B. The other is A condition on B complement. So they're different things. So it cannot add up equal to 1. Then how about this one? Can these 2 add up to 1? Yes. Because A and A complement are complement of each other. They are all conditioned on the same condition of B. So they should add up equal to 1. They should add up equal to 1. Okay, so what is the probability that it is due to a faulty design? So now, it is the probability of a faulty design or probability of a faulty design given that which probability are we supposed to find? So look at the second line. So now we see something has happened. The house collapsed. So this is an event that has occurred. We have some additional information. So now, what is the chance that the design is faulty? So it should be this one that we want to compute. All right? Okay. So here it is. So we have all this, right? And we want to compute probability of B given A. B given A. This, we saw the house collapsed, and what is the chance that it is from a house have a faulty design. So we apply the conditional probability and got it 0.9870. All right. So what does that mean? It means that if we have no information, we do not see whether the house collapsed or not, then the chance that a house with a faulty design is very small chance. But then once we saw it collapse, then it's likely that the design is faulty. It's increased to 98%. Okay? Now, I think I skipped example 2. All right? You can read it yourself. Identify what are the events that we are talking about. So as you can see that I already list out here in the solutions. So what is B and what is A1? All right? So B and A1. In addition, you will have B complement and A1 complement. So this referring to what? And then try to link up the probabilities with all this event here, and then translate the question here. These are the questions into a probability statement involving those events that we defined. All right. So I skip this one. You can work out. Okay. Example 3. So here we have 3 cards. They are identical, except that the colors are different. So for the first card, okay, both sides, except that the first card, both sides are red, while the second and the third card with one black and one side red and the other side black. Oh, sorry. So the second, both sides of the second card are black. All right. And the third one is one side. Okay. So you can think of it. The first card, you have red and red. The second card, we have black and black. And the third card, one side red, the other side black. All right. That's what you have. Okay. So now, we mix up these 3 cards and then draw 1 card and put on the table to show the face. So the upper side show is a red color. That is what we see is a red color. So we asked, what is the probability that the other side is a black? Seems very complicated. So basically, it's just saying that you ask if you see a red on the top surface. Then what is this card being the third card? Because only the third card will have a black color. Okay. Now, what are the events here? What are the events in this question? We take a card. Take a card. All right? So this card can be first card or second card or third card. All right? So we're talking about the event, which card that you take from this box. There are 3 of them. Okay, so that's the which card you take. Then once you take the card, you would like to know, okay, the upper face, whether it is red or blue. Okay? So what we are going to do is to let AI to represent the I card being drawn. or select. Then B be the upper face, upper side of the card is red. All right? That's important step. Once you're able to identify the events, then you can consider the probabilities from the given information. Then you can proceed to calculate the required probability. So, what is the probability getting the upper face? The upper face is a red color. Are we given that number? Okay. Before we answer that, let's go back to look at the numbers given to us. Yeah, no numbers. So what to do? So ask yourself, if I take a card, so what is the chance that I got A1? What is the chance that I got A2? What is the chance I got A3? No numbers there. Choose randomly. And that's important. Saying that each card have equal chance of being selected. They have equal chance. So still have no number. But we know that there are only 3 cards. And they're equally likely. So the probability of all this, probability A1 plus probability A2 plus probability A3 should equal to 1. Therefore, each one is 1/3. 1/3. So in other words, probability of AI equal to 1/3. All right? Then how about the red card? How do I get the probability of red card? We don't know. We need some computation. But do we know that if that card is a red card, if it's the first card being chosen, what's the chance that it's a red card? 1, right? Because both sides are red, no matter what you do, you will get a red color. All right. So in other words, I cannot answer the question, what's the chance of the upper face is red? But if I know it is a first card, then the chance is 1. Similarly, if it's the second card, the chance is 0. The third, it is. So this is the probability of A's, and this is the probability, given that it's first card, the chance of getting a red face, upper face is 1, this is 0, and this is 1/2. So now we have everything, although it's not given, but with a simple calculation, we can work out all this probability. So what we want is that, okay, now I see a red card. So what's the chance that it is card 3? How do I know it's a card 3? Because we asked what's the chance that if I see a red upper face, then what's the chance that the below is a black card? And there are only one card have such property. That is the card 3. So it's equivalent to I see B has occurred. So what's the chance that you got A3? All right? It's always easy for when someone tells you, this is the one. But you have to think about it. How to translate it. It did not say, okay, what's the chance getting a third card if you see a red upper face? It asks you, what is the chance that you see a black face below it? If you see the upper face, it's the red card. So this translate is the probability of A3 given B. So we apply the Bayes rule and got the answer is 1/3. 1/3. All right? So, all right? Now, what is this? The chance of getting a third card, 1/3, right? After we do so much work, and also probability A3 is also 1/3, which means that whether you see this as a red card or not, the chance is still 1/3. So what does that mean? It means that A3 and B are independent events. That means the information that B has occurred will give you the same probability of A3. All right. But the same cannot say for this. You may calculate what is the probability of A2 given B, and what is the probability of A1 given B. All right. Then check whether they are equal to probability A2 and probability A1. They may not. All right. It just you're aware that this happens to be correct. Whether a condition on B or not, the answer is the same for this particular A3 and B. All right, example 4. This is a very commonly used example to illustrate this Bayes theorem. So it usually goes like this. You have an individual, whether he has a disease, has a particular disease or not. All right. So that is the sort of first stage. Then you go for a test, and you go and say, doctor, this is not, I'm not comfortable at this pain, that pain. Then they will ask you to do some test, right? Blood test or whatever test. Okay. So the test will show you whether you have a positive result for a certain disease. So usually you go there, presume that you have or you do not have the disease, and go. The next stage is go for the test, and then you have an outcome or the results, whether it's positive or negative. So usually it goes like this. All right. So here is that a certain disease, a rare disease. So it's only affect 1 out of 1,000. So in other words, if you select one individual in the population, the chance that he has the disease is 1 over 1,000. And majority, 999 over 1,000, they don't have the disease. Then this test, test kits, all right, test, and when an individual actually has the disease, that means condition on this individual has the disease, then you will see a positive result being 99% of the chance. There are no 100%. It's not, there may be error. So 99% supposed to be very good already, maybe 99.9%. It seldom go to 100%. Then, don't forget, for someone who do not have this kind of disease, the test kit may also show a positive result. All right? And the chance is 2%. It's very small, only 2%. So in other words, even if you don't have that disease, and you go for a test, then there's still 2% for this particular test kit. There's still 2% to show that you have a positive result. So a randomly select individual is tested and the result is positive. What is the chance that he has the disease? So in this case, what are the two events? The first one is whether an individual has the disease or not. Okay? Has the disease. The complement is saying it does not have the disease. What is the second event? The second event is about this test. All right? It's not just gone for a test. It's the outcome of the test, whether it's positive or negative. All right? So in other words, I can have a disease, and whether the test result is positive or not. So don't have the disease, or the test result is negative. All right? In fact, for a test, it's either positive or negative or what? I always ask you, yes, no, I don't know, right? So a test also have I don't know. And we don't use the word I don't know. The test will not say I don't know. So they will use inconclusive. That means the three possibilities. The test will show positive results, negative results, or inconclusive results. But to make it simple for us, here we only have two outcomes, and either positive or negative. But I just let you know that is in practice there may be a third possibility for a test, inconclusive results. All right, positive, negative, or inconclusive. Okay, so this means that this 1 in 1,000 means probability of a disease is 0.0001, and this 99% is for those who have the disease. Then the result is positive, is 0.99. Then this 2% is the probability for those who do not have the disease and have a positive result, which is 0.02. Then, what's the question? The question asks us to compute the probability given that the result is positive. If the result is positive, that means given the result is positive, what is the chance that the individual has the disease? So we are asked to calculate this one. All right? It's not 0.99, huh? Positive given D and D given positive are two different things. Okay, so first step, we calculate, I use B. So we calculate this one. This one, if following my notation that I used just now, then it will be D given positive. So we want this one. So applying the Bayes theorem, so we work out the probability. Just remember, this looks complicated, huh? But basically this one is to calculate the probability of B. Probability of B, positive result. So the answer turned out to be 0.0472. Now what does it mean? So the test result is positive, but the chance that this individual has the disease is about 5% and not 100%. Right? So what does it mean? It means that if we select an individual from the population, the chance that this individual has the disease is about 1 over 1,000. But if after this individual go for a test and the test result is positive, then the chance that this individual has the disease will now is no more 0.0000301, increase to 0.05, about 0.05, 0.047. But also, it also tells you that even the test result is positive, it's not 100% you will get the disease. You have the disease. All right? Yeah, why is that so? Should I trust this test? It's not 100%. All right? The reason is that you can, because there is quite a high chance that even if you don't have the disease, you still have 2% chance that you will show a positive result. And this is called false. I mean, these are the false results. You don't have the disease and the test says that you have the disease. So it's a mistake. 2% chance. So that's why you have such a thing. Now, maybe I talk too much words. So let's look at the picture. Tree diagram. Okay, I would say that tree diagram is useful if you use it properly. But sometimes the tree diagram may be so complicated that you don't want to use the tree diagram. Okay, we start with the basic node. So an individual, and then whether has a disease or without the disease. So each node represents an event. So start selecting an individual, look at it whether it's a disease or not. So the branch lead to this node. And this is the probability go to that node. And each node will have a few branches, a few lines drawing out. And each line should have a probability. Maybe 0, but should have a probability. All right? So the sum of all these probabilities coming out from a node should equal to 1. So these two should add up equal to 1. And then after a disease, okay, whether the individual has the disease, we go for a test. And the outcome is whether it's positive or negative test results. And these are the corresponding probability. Similarly for the other part. All right? So these are the end results. We see a positive test result. This positive test result can come from someone with the disease or someone without the disease. That means an individual may go through this path to get a positive test result or go through this path to get a positive test result. And the probability of getting this positive result is equal to 0.99 times 0.001. And this one is 0.02 times 0.999. So these two add up together is the probability of getting a positive test result. All right? So you asked, now I see a positive test result. Whether it's go through this path, which means that the individual has the disease, or go through this path, the individual does not have the disease. Which path it comes from? So we have to work it out. So it will be this probability over the sum of these two probabilities. So that will tell you the chance that it goes through this path. Right? So that's how the tree diagram can be used. Okay. Now, example 5. So the student answer MCQ exam, and there are 4 possible answers. And suppose he knows the answers to each question with a probability 0.8. Right? Maybe he does not work hard enough. Sir. If you work hard enough, 1, I know the answer. Right? 4 answers. The other 3 are just nonsense. So pick the right answer. Okay, but he only knows with a probability 0.8. Okay, so if you don't know what to do, you guess. But mind you, if marks will be deducted for the wrong answer, then may be different, the approach. Will you guess? You have to think about it, right? That's what will lead to the expectation. We'll discuss it. You see, okay, just one question, 4 choices. I don't know the answer, I just pick 1. All right, so the chance being correct is 1 over 4. All right, so if I answer correct, I got 1 mark. All right, but if I answer wrongly, no penalty. Okay, I don't get any mark, 0. But if you are told that you answer wrongly, it will deduct 1 mark. Wow, then I better don't answer. All right, because it's likely that the answer I pick is wrong. The chance being wrong is 3/4. So why bother to guess? All right, so you have to, all this will lead to the consideration of expected value. At this point, we don't talk about it yet. All right, so it just, whether you know it, if you know, you get the right answer. If you don't know, you guess. All right. Okay. So here, what are the events? The event is that whether you, for a given question, whether you know the answer. All right? Then another event is what? Whether you answer correct or not. All right? So whether you answer it correctly or not depends on whether you know the answer or not. If you know the answer, then you get it right. Probability is 1. Condition on, you know the answer. If you don't know the answer, then what? You guess. Then, condition on you guess the answer, the chance of correct is 1/4. Why 1/4? Because there are 4 answers that you can pick. So 1/4. So let me ask you, if there are let's say 20 questions. I don't study, I did not study, and I want to guess all 20 questions. What's the best strategy? I just pick all answers once, or I just randomly select. Which one is better? Okay, so let you think about it. All right. Okay, so now the student answered correctly the questions. So what is the chance that he really knew the answer? In fact, this is what we want to find out. All right, so you get your answer correctly in the exam, right? So you may got an A, but maybe just by luck. But how likely you got an A if you don't know nothing? So we try to set it very small chance. Maybe you still can get it. All right. So those who study should get an A. Study know everything should get an A. So that's how exams should be designed. Okay. So the fact is that they answer correctly. It does not mean that he knows the answer. It can be just guessed correctly. So we want to figure out. So this is how we do it. And apply the Bayes theorem. It turned out to be 0.94. So not that bad. All right. So it knows the answer is probability A1 is 0.8. Okay. That means we are assuming that without the exam, these students will know the answer with probability 80%, maybe from the CA or whatever, right? So in other words, without this test, without these exam questions, okay, these students will know the answer with probability 80%. But now we go through this answering this question, he got the right answer, the correct answer. Now the chance that he knows the answer is increased from 80% to 0.94, 94%. All right. So not bad. So this exam questions are designed to test, to enhance its probability of answer correctly. All right. Okay. Okay. Example 6. Okay, I don't go in details. But this example, what are the events? So basically, we take items, defective components. So we have some items, whether it's defective or not. All right. So among all the batches, so you have various batches, half of them has no defects. 30% of them has 1. And 20% has 2. So how many batches? What's the proportion of batches have 3, 4, 5 defectives? 0, right? Because this adds up to 100%. All right? Okay. So now we select 2 batches from a batch. All right? Just take 2 items and check whether they're defective or not. And we find out that, okay, no defectives. The defective is 0. So we ask, what is the chance that it is from a batch with 0 defective and from a batch which is 1 defective or 2 defectives? All right. So basically, it's like this. We have batch, and don't know whether this batch belongs to the no defective or 1 defective or 2 defectives. All right. If I don't take out something to test to find out, I just say that okay, half a chance that it is no defective batch, 30% or 0.3 chance that it is 1 defective in the batch. But now I select this batch, I take out 2 items and find that there are no defects. These 2 items both are non-defective. Then I ask, what's the chance that this batch is coming from a batch with no defects or coming from those batches with 1 defect? items, defective items, or 2 defective items. So that's what the question asked. All right. So let AI be the I defective. There are I defectives in the batch, and DI is I defective in the sample. Because we take 2 samples, so the I equals 0, 1, 2. From what we are given, these are the probability of AIs, and you select 2 items, right? 10, where is this 10 comes from? Huh? Oh, okay. Thank you. Batches of 10. Oh. Yeah, you see? I don't understand English, right? TEN, it's not 1, 0. Difficult to see. Okay. All right. So, a batch consists of 10 items. We select 2. So, what is the chance that it has 0 defectives and 1 defective and 2 defectives? So, it's easy to compute using counting method. So these are the probabilities, all right? And then, so this referring to if it's from a batch with no defective item, what is the chance that you got no defective? Of course, the chance is 1. And similar for the others, all right? Now, here, this one, how to get this one? This one is a 10 items, 9 of them are perfect and 1 defective. So because you don't want to have, you select 2 without any problems, so the 2 must taken from the 9 non-defective items. And you don't take any from the remaining 1 defective item. That's the number of ways that favor to no defective item from the batches with 1 defective items. So this is how you got the answers. Then apply the total probability law, and you get that the chance of getting no defective items, all right, from the for the 2 items is 0.86. So now this is what I see. I check. Probably A0 given D0. So it's 0.5784. Now remember, probability of A0 is 0.5. Without doing anything, we are told that the batch is 0 defectives with probability 50%. But now we take this batch and check, and then take out 2 items and check, and there are no defectives. So it increased the chance that this batch in fact comes from the batch with no defectives. From 0.5 increased to 0.784. Similarly, the probability of A1 supposed to be 0.3, but now it reduced to 0.2776. All right. And this one, A2, supposed to be 0.2. It also reduced to 0.4144. So in other words, I see from these 2 items no defectives. So I increase my bet, or I believe, or the probability change for A0, increase from 0.5 to 0.57, while the other 2 decrease. This number plus this number plus this number must be equal to 1. They are conditioned on the same condition, D0. And A0, A1, A2, okay, add up equal to the sample space. Because all the patches is either no defective, 1 defective, or 2 defectives. This is a very interesting problem. We even give a name called Monty Hall problem. It is a game show, maybe long before you were born. Okay, it's like this. In this game show, there's the player, okay, have three doors that he is asked to open one of them, and these three doors, the first one, not the first one of them has a big price, and at that time the big price, all right, and the other two, not so bad, it's not empty. The other two doors behind it is a goat. All right. So, not that bad. You open the door, you got a goat, and you bring the goat home. All right. Whether you want to raise it or whether you want to eat it, that's for Chinese, right? Up to you. If a car, of course, car is more expensive. Now, the game is like this. So, first of all, the game host asks you, oh, pick a door. I pick this door. And he will not open the door for you to see whether you got the car or not. What the host does is, okay, you choose this door. He opens another door, which you don't choose. You did not choose. All right, the player did not choose. Open the door. So do you think that he will open the door with a car behind it? No, definitely. If you open it, then the game is over, right? He must open the door. We know that definitely is a goat behind it. Now here's the most crucial part. Then the host asks the player, you want to switch your choice or not? So will you choose to switch or stay with the original choice? Switch, sure? Because you read my notes? Okay, yes, the answer is that you need to switch. But as I told you, knowing the answer is not good enough. You must be able to explain why you need to switch. All right? So, here it is. All right? Now, all this I just explained. Now, okay, so stick to the strategy. That means I pick one and I stick with it. I don't change. All right? So because I just choose randomly, there are three doors. I choose one of them, so it's 1/3. All right? Okay? So it's likely that a door with a goat with 2/3 chance, right? Now, if I stick with my choice, all right? So in other words, if I pick the right door, I stick with it, I will win. I don't care what the host does, all right? But if I pick the door which has a goat behind, I stick with it, then I won't get my car, all right? So the chance is 0 to win the big prize. So it is 1/3 times 1. This 1/3 is the probability you select the winning door. All right, let's put it this way: winning door, the door with a car behind. Then if you stick with it, the chance, given that you don't switch, then you still you win the prize with 1 probability. Okay, let me put it this way: 3 doors, right? Behind it is a car, a goat, a goat. So suppose you pick up this one with 1/3 probability. You stick with it in the second stage, the host open 1 door, but then you stick with it, then you will get the car when you open it. All right. But if you select this, then when you open the door, you're very disappointed you got a goat inside the car because you stick with it. All right. So this is what it means. 0 is because you stick with that door. The door does not have a car behind. Changing. How about switch strategy? So I choose the door with probability 1/3 that with a car. All right. So if I switch, then I lose. All right? That is, if this is a car, a goat. All right, I pick up this one, and now I change my mind. After I see what happened, then I change to this one. Then I lose because I pick up the door, I switch to a door with no car behind. So 1/3 of chance that you select the winning door, but then you switch, you lose. But there 2/3 probability that you select one of these. Now when you switch, you switch because one of the door lead to a goat already open. When you switch, definitely you will switch to a door with a car behind it. All right. So suppose I choose this one. Then the host will not open this door. It will open this door. So I switch. I have no choice but switch to this winning door. So definitely I will win. All right. So the probability is 1/3, which is when you choose the winning door, but you switch, becomes loser. All right, 0. But if you choose the door with a goat, 2/3 of the chance that you will pick that door. There are 3 doors, 2 of them with a goat. When you pick one of those with goat, 2/3 chance. But once the door open with a goat, you change. Definitely you will change to a door with a winning strategy. So you have 2/3 chance of winning. So switch. All right, so you see, that's why you need to know probability and statistics. So next time when you have in such game show, you know the strategy, switch. All right, don't stick to your own. Or let's put it this way. If you don't switch, what does it mean? It means that the information to you, open the door. Open the doors will show you that there's a goat behind it. Makes no difference to you. All right, you don't use that information to modify your chance. All right, so it's still 1/3 because there are 3 doors. Just like nothing happened, you stick to your door. But once you switch, it does not mean that you will enhance your chance, but it will change. The information may help you to increase, not help you to increase, but will change the probability. It can be increased, can be decreased. In this example, it increased the chance because we make use of the information by switching the strategy. Switching the choice. All right. So my point is, sometimes information given to you, in this case, is a door is opened, shows you a goat. All right, that information may help or may not help. In this example, it helps us. All right. Okay, so you can watch the real thing about this game or discussion. All right. So, independent events. Very, very important. Conditional events or conditional probability are so complicated. Independent events make life a little bit easy, simplified. All right. Okay. So we toss 2 fair die, or a fair die tossed twice. All right. A is that the first toss show an even number. B, a second toss show a 5 or 6. All right. So these two. So the number of possible outcomes is the number of that for tossing a die twice is 36. All right. Then for A needs that the first one is even number. So you pick between 2, 4, and 6 for the first die. Then the second time. The second time, you can pick from 1, 2, 3, up to 6. All right? This one is 2, 4, 6. So altogether, there are 18 times, or 1/2. All right. Let me repeat this again. There are many ways to obtain the probability. So in the previous session, we talked about counting the number of ways favor event A, the number of points, sample points in the sample space, all this based on the counting. But we can also use the properties of probability or conditional probability to get the answer. So in this case, I still use counting. All right. But if you think of it, basically, you are talking about the probability of the first die. If you know that they are independent, then the first die getting an even number is 1/2. Then the chance of getting this, we did not specify anything about the second die. So the second die can be any number. So the probability is 1 for the second die. And the two are independent. So we multiply them together, we'll get 1/2. All right. But here is, we are basically counting the number. So also do for B, it is 1/3. And it turns out that these two numbers, when you multiply them, it gives you 1/6, which is the probability of A intercept B. So in other words, if two events occur together, that means A intercept B, the chance of this event A intercept B occurs is equal to the product of A and B, product of probability A and probability B. Then we say that these two events are independent, which means that what happened to A, whether A has occurred or not, and what happened to B, whether it has occurred or not, they are independent. All right. We will not have any impact or any link among these probabilities. All right. So if you have such thing, you can work it out. Probability of A condition of B is 1/2, based on the definition of conditional probability. But on the other hand, we just show that probability of getting the A is equal to 1/2. So they're the same. So this is another definition of two independent events. If the event A has a probability is the same as the conditional probability of A given B, then B and A are independent. All right? Or the probability of B is equal to probability of B given A. All right? Now it's a bit confusing. So you just have to remember, without the condition, sometimes we refer it as the marginal probability. That means we don't have any conditions. All right? But then if you condition on something, find out the probability. In general, these two probabilities, probability of A and probability of A given B, in general, they are different. Unless A and B are independent events. That means they have this property that one and the other are not of link. All right? So we call it independent. Sometimes people just refer it as statistically independent. All right? You may be independent from your parents, right? Financially. But here we say that two events are independent. It means that the probability of A intercept B is equal to probability of A times probability of B, or the conditional probability of A given B is the same as probability of A. Okay. So, all right, so this is the definition. Remember, independent events cannot be shown in the Venn diagram. Don't try to use the Venn diagram to prove two events are independent. You have to follow this definition, or the other definition is like this. A given B is the same as probability of A, or B given A is the same as probability of B. These three things are the same. These three statements are equivalent. So you just have to check one of them. Depends on which one you know. So if they're not independent, then they are called dependent events. All right? So here are some properties. If probability A bigger than 0, probability B bigger than 0, what does this mean? Remember, probability of an event is range from 0 to 1, including 0 and 1. So here we just say that A has a chance bigger than 0 to occur, which means that A is not an impossible event. All right, no 0. Probability of A is not 0, probability B not 0. All right. Then A and B are independent. Then what we have is this. All right. This just follows from a definition. Remember, this one equal probability of A intercept B divided by probability of A. All right. All right. But because they're independent, all right, so the multiplication rule saying that this equal to the product of this times this. But according to the independent event, this probability is equal to this times probability of B. Therefore, these two must be the same. All right. So that's another definition for independent events, and also it is intuitively saying that the condition on A probability and without the condition are the same. So it doesn't matter what A has occurred or not. So that's intuitive meaning of independent events. All right. So if both are bigger than 0 probability, then if they're independent, then they cannot be, okay, they cannot be mutually exclusive. It's hard. Independent event and mutually exclusive event are two different types. They are not related. Not one implies the others, or not equivalent. All right? Why? Because from the independent event, because we are given that A, B are independent events. So this equal to this, right? But at the same time, we assume that these two probabilities are bigger than 0. Therefore, the product of it is bigger than 0. So can we say that A and B are mutually exclusive? No. Why? Because if they're mutually exclusive, what can we say about this probability? It has to be 0. But now we say that it's not 0. It's bigger than 0. So therefore, it cannot be mutually exclusive. So come to think of it. For mutually exclusive, what does it mean? It means that if A has occurred, B cannot occur. Right? Because there's nothing common to A and B. If we know that A has occurred, so look at all the sample points in this A thing belong to B. So B will not occur. All right? So we definitely know what happens to B. All right? If A has occurred. So it's cannot be independent. Independent means that with the knowledge of A, you still cannot tell whether B has occurred or not. So that is basically what we mean by independent. All right? Okay. Same. Mutually exclusive events does not imply, if we have two mutually exclusive events, then these two events cannot be independent. Follow from the definition. So we start with mutually exclusive events. So probability A intercept B is equal to 0. But since these two are bigger than 0, then the product must be bigger than 0 because of that. All right? So this is bigger than 0, but this one is equal to 0. The two cannot be the same. So therefore, it cannot be independent. Cannot be independent. What's this statement and the previous one? The previous one saying that if you have two independent events, then it cannot be mutually exclusive. Okay? If you have two mutually exclusive events, then they cannot be dependent. Okay? All right. And sample space as well as empty sets are independent of any event. What does it mean? It means that if I have an event, all right, which is impossible, then it's independent of any other event. All right? So suppose I toss a die, 1, 2, 3, 4, 5, 6. What is the chance getting a 7? An event is getting a 7. Impossible, 0. Then I ask you, what is the chance an event getting a 7, an event getting an odd number from toss a die? Are they independent? Of course they're independent, right? Whether this 7, we know that is sure it will not happen. So this 7 has occurred or not has nothing to do with this even number. So they're independent. All right? We can show it mathematically. Okay, it's like this. Okay? So it's fun to do mathematics. Huh? So even if you don't know the interpretation, you can still prove that. All right? First of all, A intersect S. S is all the sample space is equal to A. All right? So I can write probability A times probability S. How can I do that? Because this is 1. So this equal to this. Therefore, A and S are independent. Right? And how about empty set? Empty set, A intersect empty set is still empty set. All right? So probability empty set times probability A. How can I do that? Huh? What is this? Probability A is not 1. 0 times 1 or times 1 times 0.5. What's the answer? It's still 0. All right. So multiply 0 with any number is still 0. So multiply probability A. So they are independent. If A is a subset of B, then A and B are not independent unless B equal to S. So in other words, if A is a subset of B, but B is not the whole set, if the whole set then it's independent. But it's not, then A and B are dependent events. All right? So again, it's very straightforward to prove. We want to show that this does not equal to the product of these two. So A intercept B, according to this given condition, is equal to probability A. All right? Probability A does not equal to probability A times a number, which is probability of B. And this probability B is between 0 and 1, and does not equal to 1. Unless this equal to 1, then this is correct. This is equal. Unless this one equal to 1. And it's only equal to 1 when B is equal to the sample space. You see, mathematicians like to do things like this. I have this condition, A is a subset of B. Then I show that this A and B are dependent, which means that the probability of A intercept B does not equal to probability of A times probability of B. All right? But is this always true? Not equal. Is it always true? No. There's one exception. So they pinpoint this exception. Is when I say A equal A times B. All right? This in general is not equal. But what happens if B equal to 1? Then this is correct. So that's why I specified that, okay, unless probability of B equal to 1. But if probability B equal to 1, what does it mean? Means that B, in fact, is the sample space, S. All right? Okay. So just to emphasize again, you cannot show the independent events using a Venn diagram. That means cannot draw the picture. And second thing, because it does not, you cannot obtain or cannot show the independent events through a Venn diagram. So sometimes your intuition, okay, your intuitive feeling about whether two events are independent or not may be wrong. Then how can I show two events are independent? Follow the definition. Show that the probability of A intercept B equal to the probability of A times probability of B. Then they are independent. All right, so stick to this rule. And mutually exclusive events are dependent events. Okay, then we follow with some examples, simple example to illustrate. Okay, we can have mutually exclusive event and also dependent events. Okay, we can also show that there are mutually exclusive, not mutually exclusive events and not independent events, and so on. Okay, here is an example. Just toss a die. Event A, odd numbers. Event D, even numbers. So A and D are mutually exclusive, no intersection. And probability A intersect D is equal to 0. No common point, so this is 0. So the product of probability of A and probability of D does not equal to the probability of A intersect D. So therefore A and D are dependent events. All right? They are not independent events. And they are mutually exclusive. Mutually exclusive and not independent events. Now, we can have not mutually exclusive and not independent event. So I consider A, still the same A, but now B is a number less or equal to 3. 1, 2, 3. So therefore, the probability of A is 1/2, probability of B is 1/2, probability of A intercept B, which is 1 and 3. 1 and 3. So it's 2/6. A intercept B is 2/6. So the product of this does not equal to 1/3. So A and B are not mutually exclusive, and A and B are not independent. Right? Okay. Then another example to show this time, not mutually exclusive, but independent. So we still have this A, but B, sorry, not B, C. C is an event that we got a number less or equal to 4. So A intersect C is still 1 and 3, so it's 2/6. All right, but A and C are not mutually exclusive, but probability A is 1/2, probability of C is 2/3, and the product of it, the probability A intersect C is 1/3, which is the product of probability A times probability of C. So they are independent. Do we have the fourth scenario? No, we don't. So we have showed that, we have example to show that we can find events that are not mutually exclusive and not independent. We can also find not mutually exclusive but independent. We can find mutually exclusive but not independent. All right? Only 3 cases. Okay, example 1. So straightforward. A particular person make a mistake in file the income tax return is 0.1. In totally unrelated persons, all right, each of them make a mistake. This is a little bit unrelated person, so we assume that they are independent. So the chance of getting both of them make a mistake, that means M1 intersect M2. What is this? Because they're unrelated, we assume that whether one make a mistake in filing the income tax return are independent to the other person's make a mistake. So it's equal to probability of M1 times probability of M2. Now this is very, very useful. Let me repeat it again. For independent event, the probability of the intersection of all these independent events will be much easier. It's just equal to the product of the probabilities of each individuals. All right? So, 2 persons, okay lah. What happens if I have 100 persons? How to find this one? Wow, becomes headache. If you do the countings, it's very, very hard. If you do the conditional probability, it's also very hard. But if we know that they are independent events, then it becomes very, very simple. It's just equal to probability of M1 times probability of M2 and so on. All right? It's like that. If you can further know that each individual has the same probability of committing an error in filing the income tax return, then all will be the same. Then just the number raised to power 100. So it's very useful if you have this very strong condition, independent events. All right? Okay? So, the wonderful thing about it is that if A, B are independent, so is A, B complement, A complement B, and A complement B complement. Let me put it more extreme. If I have A1 up to AN, they are all independent. All right? In fact, they are mutually independent. Then I will say C1 up to Cn. What are these C? C's can be A1 as AI or AI complement. All right? So that means C1 can be A1 or A1 complement. C2 can be A2 or A2 complement. So you just pick any n of them, C1 up to Cn. C1 can be A1 or A1 complement. Then all these are independent. The Ci's are independent. So this is just a special case. A1 equal to A, A2 equal to B. So this simply says that it is A1 and A2 complement. A1 and A2 complement. This is A1 complement and A2. This one is A1 complement and A2 complement. All right. All right. So we can prove easily that we have this result. All right. So Tom will be alive in 20 years is 0.7. And Jack will be alive in 20 years, 0.9. So I guess maybe Jack is younger, so is alive in 20 years, have a higher chance. All right? And they are not related. So what is the chance that neither of them will be alive in 20 years? We have to assume that they are not related. Hey, if they are from the same, if one is father, the other is son, they are related. Or they are married. No, not Jack, not Tom and Jack. All right. They may have the similar living habit, or maybe they're buddies or they're brothers. All right. They have similar living habits, right? Eating habits, similar life patterns, and they are not independent. But here we assume that they are independent. So what we are trying to look for is A complement, B complement. Neither of them alive in 20 years. That means they will not live, Tom will not live more than 20 years, and Jack will not live in 20 years. These two together. So it's intercept of this A prime and B prime. So that's the probability that we want to look for. Neither of them live longer than 20 years. So it's equal to probability A prime times probability B prime. So it's 0.03. All right? We did this one just to illustrate all this. If A, B are independent, so are the complement events are also independent. Not just A prime, B prime are independent, but A, B prime are also independent, and A prime, B are also independent. That's what it means. All right. So I extend it to end independent events. So n independent events. Once we go beyond 2, there's a problem. There's something called mutually independent. Or independent. And there is something called pairwise independent. Let's say if you have 3 events, it can be A1 and A2 are independent. A1 and A3 are independent. A2 and A3 are independent. But the 3 are not independent events. All right? So pairwise, just take any 2. The probability of AI intersect AJ is equal to probability AI times probability AJ. Then they are pairwise independent. And mutually independent, wow, it's terrible. N of them. If we say n events are mutually independent, it has the following properties, or you have to check the following. Take any 2 of them. They satisfy the product of the intersection of these 2 events, probability of the intersection of these 2 events equal to the product of the 2. Not just 2. You also check 3, check 4, check 5, up to check n. Wow, headache. So many have to check in order to check that they are mutually independent. All right, this is what it means. So you pick any k of them. K can be just 2, 3, 4, up to n. Then the product, then the intersection of all this with probability equal to the product of all these individual probabilities. All right. So, mutually independent implies pairwise independent. All right. And this is what you mean by mutually independent. Pairwise independence, any 3 events are independent, any 4 events are independent, up to any n event, not any, all the n events are independent. All right. So all this is true. Then, this is important. Mutually independence is very strong conditions. It implies the pairwise independent, because pairwise is part of the conditions. But on the other hand, pairwise independence, if you can show any 2 of them are independent, does not mean that all of them are independent. So here again, if BI equal to AI or AI complement, then all the BIs are mutually independent if the original AIs are mutually independent. Here is an example. All right. I toss a die 3 times. The first toss is an odd number. The second toss is an even number. And the third one gives a value greater than 4. So I've tossed it 3 times. So this is how I define it. A is an odd number obtained in the first toss. B, even number in the second toss. C, in the third toss, they are either a 5 or 6. So I work out all this probability. Now, in this case, I use the counting method. So the first die, I can have only 1, 3, and 5. 3 choices. Choose 1. Then the second toss, I have 1, 2, 3, 4, 5, 6. I pick 1. Third one. And this is the total number of choices. So basically it's 1/2. All right. Similarly for B and for C. Then you can see that probability of A intercept B is 1/4, which equal to the product of these 2. Probability of A intercept C is equal to 1/6. These are based on the counting methods. All right, but it's also equal to product of probability A times probability C. So that means A and C are pairwise independent. Similarly for B and C. So A, B, C, you pick any pair from these 3, they are independent. All right. And if you consider probability of A intercept B intercept C, it also can be shown equal to the product of A probability, B probability, and C probability. So they are mutually independent. All right. So any two independent, any three, I only have three, so any three also independent. So I can say that A, B, C are mutually independent events. All right. So example 2 is to show that it is not mutually independent but pairwise independent. So I just change example 1 by changing the event. This time I've thrown only two times, two dice. So the first die show an even number, the second die show an odd number. The third one is the 2 dice, so either both are even or both are odd. You see? It's even, odd, odd, even, odd, odd, or even, even. Right? These are the 4 possible scenarios when you choose 2 dice. So I already calculate A, B. What I need is calculate C. So both dice are odd or both dice are even. So this is how I got the number. It's 1/2. This is to consider the numbers. Okay? What I wrote down here is to consider only the sample points, even number and odd number. Here I consider the numbers, 1, 2, 3, 4, 5, 6. So this is to got all the odd numbers. First one odd, second one odd, and this is the total number of possible combinations, 36 of them. Even, even. All right? So it's 1/3. 1/2, sorry. So you can show that all these pairwise are the same. But what probability of A, B, C? The first one is odd number, is even number. The second choice is odd numbers. Then this one, you need both to be of the same. It cannot be, so these are empty sets, so the probability is 0. So what does it mean? It means that A, B, C probability does not equal to probability of A times probability of B times probability of C, which means that A, B, C are not mutually not mutually independent. They have only pairwise independent. Pairwise independent. All right. Okay, I can finish this. I still have a few slides. So I stop here and continue next week. All right. And I will upload. Have I uploaded chapter 2 notes? Yeah, I did, right? Yeah. Okay, so next week we'll finish this chapter as well as start chapter 2 on random variables.